Hi, this is Engineering Statistics and Linear Algebra 18EC44, Module 4, Lecture 9, which corresponds to the linear transformation and in particular representation of the linear transformation by matrices. In the last class, we have considered the basic transformations, and then we tried to consider the examples, which are the differentiation, the integration, and then the multiplication by a polynomial. Now, all these linear transformations, how we can represent these by means of matrices, what we will consider today. So, the linearity has a crucial consequence. If we know Ax for each vector in the basis, we know what a basis is. A basis is corresponding to a set of vectors which are both linearly independent, or also they span a set. Now, when we talk about linear independence, we should remember that it corresponds to the, in this case of basis, it corresponds to the minimal set, and the what you call for a basis, the spanning should be the maximal set. So minimal set of independent vectors and maximal set of vectors which span a space will correspond to the basis. Suppose the basis consists of, if we have in the basis the n vectors x1 to xn, then every other vector x can be represented as a linear combination of these vectors because they span the space. And once we write that as a linear combination, which we have written over here, x is equal to c1 x1 plus c2 x2 plus etc. cn xn, then we can linearly determine the value of Ax, and that Ax over here is mentioned as C1 into Ax1 plus C2 into Ax2 plus C2 into Axn, and so on. So it's a, linearity is a crucial consequence of the basis, and the linearity can be represented by this. Now, taking an example, if what is the linear transformation? What is the linear transformation when we say what is the value of A that takes x1 and x2 to ax1 and ax2? For the example which is given over here, x1 is equal to 1 and 0 goes to ax1 is equal to 2, 3, 4. If x1 goes to this ax1, and if this x2 goes to this ax2, then what is the value of A is what we need to find out. Now we can consider A as a matrix which consists of A11, A12, A21, A22, A31, and A32. Now if you consider this A and then you try to multiply this with x1, because we are considering this as a 3 by 2 matrix because of the reason that you have ax1 as the number of elements in ax1 here, number of rows rather is 3, and the number of rows in x1 is 2. Therefore, the A should be 3 by 2. Ax1 is rows 3 and the x1 has rows 2. Therefore, A should be 3 by 2. So this, if you try to multiply with this, then you'll get A11 plus A11 is equal to 2, and A21 is equal to 3, and A31 is equal to 4. Similarly, if you multiply this with this, then you'll get A12 is equal to 4, A22 is equal to 6, and A32 is equal to 8. And all those we can just substitute to get the value of A. Similarly, if we start with the basis, we have started here with the basis x1 equal to 1, 0 and x2 is equal to 0, 1. In place of that, if we take x1 as 1, 1 and x2 as 2, minus 1, then we are again going to get the same value of A, and that can be again considered by multiplying this x1, which should be in the form of the column matrix, with this. So that means it will be A11 into 1 plus A12 into 1. That will be equal to the value which is 2, and Similarly, you can keep on writing that and try to solve the set of equations for them, and you will definitely get the same values of A. So that's what is being mentioned here. A is, which is there like this, is to be multiplied with this, and then you write the set of equations. A multiplied by 2 and minus 1 will give you the value which is 0, 0, 0, and then you will get the value of A. You can just get the value of A. Now here he has put a different combination of AX1 and AX2, and hence you will get the same value of the what you call A there. So if 1, 1 transforms to this and 2 of minus 1 transform to this, we are going to get the same value of A. Now let us consider how we can represent the linear transformation, which is the operation of differentiation by means of a matrix. Now differentiation transforms a set of vectors V, which is in P3, into another set of vectors, or rather a vector space V into a vector space W, and vector space V is what you call within the polynomial space, which is P3, and vector space W is within the polynomial space, which is P2. Now, in that case, for the polynomial of degree 3, the natural choice of 4 basis vectors is, and again, the basis vector is not unique. One should remember that the basis vector is not unique. So the basis for P3 is P1 equal to 1, P2 equal to T, P3 equal to T square, P4 equal to TQ. Now this has to be transformed, or this has to be differentiated. If you differentiate this, and this is what we have, d by dt of P1, P2, P3, P4 of these values, then we are going to get AP1, AP2, AP3, AP4 as 0, 1, 2t, 3t square. The differentiation of 1 will be 0, differentiation of t will be 1, differentiation of t square will be 2t, differentiation of t cube will be 3t square. Now, you can just what you call AP1 is equal to 0. It means AP1 is equal to 0, AP2 is equal to 1, AP3 is equal to 2t, and AP4 is equal to 3t square. Now, substituting this back over here, then we'll get AP1 is equal to 0 itself, AP2 is equal to 1, and that one is P1. AP3 is 2t, and t is P2, so therefore AP3 will be 2 into P2. Similarly, AP4 here is 3t square, and P3 is t squared, so therefore AP4 will be 3P3, and that's what is mentioned over here. Now this what you call set of equations for AP1 to AP4 can be represented in this way. AP1 is equal to all zeros because we have 0 here. AP1, AP2 you can see is equal to P1, so that means coefficient of P1 should be 1, and all the other the coefficients of P2, P3, P4 should be equal to 0, and that's what we have mentioned here: 1 of P1 plus 0 of P2 plus 0 of P3 plus 0 of P4. Similarly, the AP3 is 2P2, that is coefficient of P2 is 2, otherwise the coefficient of the what you call P1, P3, P4 will be 0, and that's what is mentioned over here. Similarly, AP4 is 3P3, coefficient of P3 is 3, and all other coefficients are zeros over here. So this whole thing over here can be written in the form of a differentiation matrix 0, 1, 0, 0. That is mentioned over here. Coefficient of P1 come in the first row, coefficient of P2 come in the second row, coefficient of P3 come in the third row, and coefficient of P4 come in the fourth row. And thus we can generate the differentiation matrix, which is like this, from the values being specified over here. Let us take another example of a polynomial, which is p equal to 2 plus t minus t square minus t cube. Now, if you try to differentiate this, you are going to get 0 plus 1 minus 2t minus 3t square. So again, that can be, what you call, if you try to write that, then we'll get here the 2, 1, -1, and -1 is what we have here for the input side, and the what you call AX value, which is the differentiation of this, AP value or AX value, which is the differentiation of this, which turns out to be just this itself, 1 minus 2t minus 3t square. That is constant 1 minus 2 coefficient of t minus the coefficient of t square, and the coefficient of t cube is not there here, so therefore we write a 0. And to get this from this, you need to derive this value. So this is an exercise you can consider and try to derive this by the same method whatever we have followed in the earlier example. So as a, on the whole, one can say that suppose we have the vectors x1 to xn, which are the basis for the space V, and vectors y1 to ym, which are the basis for W, then each linear transform T from V to W is represented by the matrix A, and the jth column is found by applying the transformation T to the jth basis vector xj and writing txj as a combination of y's. And column j of A is nothing but txj is equal to axj is equal to a1jy1 plus a2jy2 plus dot 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 amjym. Similarly, how we can represent the operation of integration, which is again a linear transform by means of a matrix, is what we'll try to see now. So here, integration transforms V is equal to P3 into W equal to P4. And this, we can choose the value for the what you call input side as P1 equal to 1, P2 equal to T, P3 equal to T square, P4 equal to T cube, and P5 is equal to T to the power 4. So if you differentiate this what you call, if you integrate this P1, P2, P3, P4, that is 1, T, T square, and T cube, then you are going to get the, integration of this will lead to AP1, AP2, AP3, AP4, and integration of 1 is T, integration of T is T squared by 2, integration of T square is T cube by 3, integration of T cube is T to the power 4 by 4. So AP1 is what you call T, and that T is nothing but P2. That's why we have AP1 equal to P2 here. AP2 is T squared by 2, and T square is P3. Therefore, AP2 is P3 by 2. AP3 is T cube by 3, and T cube is P4 here. So therefore, AP3 will be P4 by 3. AP4 is T cube by 4. T to the power 4 by 4, and T to the power 4 is P5. Therefore, AP4 is equal to P5 by 4. Now, each one of this AP1 equal to P2 can be represented in this way because we have the coefficient of P2 as 1. So 0P1 plus 1P2 plus 0P3 plus 0P4 plus 0P5. Here AP2 is having P3 by 2, that is the coefficient of P3 is half, and hence we can write this AP2 like this with the coefficient of P3 as half and all the other coefficients as zeros. AP3 here is having the coefficient 1 by 3 for P4, and that is what is mentioned here. Similarly, AP4 is having the coefficient of P5 as 1 by 4, and hence we have here 1 by 4 as the coefficient of P5, and all the other coefficients are zeros. So again, we can try to write the integration matrix using all these over here. And this 0, 0, 0, 0 goes into the first row, this 1, 0, 0, 0 goes into the second row, and this 0, 1, 0, 0 goes into the 0, half 0, 0 goes into the third row, then 0, 0, 1/3, and 0 goes into the fourth row, 0, 0, 0, 1/4 goes into the fifth row. So thus we can generate the integration matrix which is specified over here. So on the whole, we can say that integration followed by differentiation brings back the original function, that is a differentiation, what you call, if it just means that first we take the a differentiation, uh, we take the integration first and then the differentiation. Um, then we will just get the value back. To make that happen for the matrices, if we do the differentiation of the above, that is whatever we have got here, this thing, or rather this thing, if you differentiate this, then t squared by 2, t cubed by 3, t 4 by 4 will get 1, t square and t cube. That just means that you can try to represent the whole thing by the proper way. Then the differentiation, we get the differentiation matrix as a 4 by 5 vector, which is something like this: 0 1 0 0 0 0 0 2 0 0 0 0 0 3 0 0 0 0 0 4. So if you take the differentiation, if you take the integration first and then the differentiation after that, then the combination a diff a int will be equal to I, and that is this. So that means this multiplied by the value over here, okay, will be equal to I, and we will get this. This is a 4 by 5 matrix, and this is a 5 by 4 matrix. So 4 by 5 into 5 by 4 will give us a 4 by 4 uh, matrix, which is in this case a identity matrix, However, we see that the a differentiation and multiplied by a integration will give I. That is, differentiation is the left inverse of integration. But rectangular matrix cannot have two-sided inverses. That is, for a rectangular matrix, a int a differentiation does not exist. The reason being that if you take a rectangular matrix, then you are going to get uh, you can't get the value at all. For a square matrix, which is what we have in this case, then a in a differentiation will not be equal to I, because of the reason that if you try to what you call multiply the other way around, that is, this is multiplied with this over here. So this is a 5 by 4 matrix, and this is a 4 by 5 matrix. If you multiply this, you'll get a 5 by 5 matrix, but you're going to get the first what you call column as all zeros. So because the first column has all zeros, that is, the 5 by 5 product will have all zeros in the first column, you are not going to get back the original thing. So that is because the derivative of the constant is 0. So in the other columns, a int a differentiation is the identity, and the integral of the derivative of Tn is Tn. You will get that, but only the missing term will be over here. Hence, we say that for the square matrix, a int multiplied by a difference is not equal to I. But it will be, in the first column, it will be equal to 0. Now, that can be considered something like this also. We have considered in the what you call yes. So if we take this, if we, after differentiating, you'll get this. If you try to integrate this here, now this 0 integrated will give us the value C. It will not give us the value 1 exactly. C can be anything. C can be either 0 or 1 or 2 or 3. Whereas if you integrate 1, you'll definitely get a T. If you integrate 2T, you'll get definitely T squared by t squared, and if you integrate this t 3t square, then you will definitely get the value t cube. But if you integrate the value what you call 0, then you are not going to get a value 1 exactly. You'll get a value constant, and that can be anything. That is why we say that that's another way of taking that the a int into a differentiation will not be equal to I. With this, we come to the end of the lecture for today.